Hello everyone, my name is Eran and I'm from the University of British Columbia in Vancouver. This is joint work with Eldad Haber, and as Stephanie said, it's about the Helmholtz equation for a point source. So we'll start with an introduction. We'll see some reformulation of the problem into a complex valued advection diffusion reaction equation. We'll basically split the problem into two. One of them is the Eikonal equation, the first part, so we'll talk about the solution of that equation. And then we'll use multigrid to solve the ADR equation for basically the amplitude. At the end, we'll see some numerical results. Currently, we have only 2D simulations, and in the future, we'll have 3D. So consider the Helmholtz equation with a point source. So that's the usual equations that you know. Omega is the kind of like the frequency, and k squared, k is the medium that varies in the domain. We solve this problem for a point source at x0, so it's a delta function, and we assume boundary conditions that the solution goes to 0 as we move far away from the source. So it's an indefinite linear system, quite well known. It is considered to be difficult to solve, but still there are many multigrid approaches. There is wave ray. One of the most common or famous solvers is the shifted Laplacian approach, but we'll stick to the red approach is the ADR formulation that was suggested by Haber and McLachlan in 2011. There is a recent work about LDU approach by Enquist and Paulson, which is quite serious, but we want to do it with multigrid. So all of these approaches are for general right-hand side, but we'll solve the problem for a point source, and by that we'll simplify it a little bit. And why we're interested in point sources? Because in seismic exploration, we're mostly interested in solving this equation for point sources. So you can look back at Keith Kelly's talk yesterday. He talked about it quite a bit. And there actually are papers for solution for point sources, specifically for point sources. Now, solution for point sources mostly divide the problem into several, or more or less two, hopefully easier parts. So that will be our approach. So we decompose the solution U into the amplitude and the phase, basically. The phase, the tau of x, is also called the travel time, or first arrival time of the wave. And now we have double the unknowns. So if we put tau equals 0, then we get a equals u, and we get the same equation back. So now we apply the chain rule for u, so we take the gradient and the Laplacian of u with respect to x and put it all in the equation, and we get this advection reaction diffusion equation for the amplitude basically. So the recipe by Haber and McLachlan said, choose tau basically as you please. So the resulting ADR problem can be solved by multigrid. And since we double the unknowns, so we can choose tau as we please. So A, the amplitude, will absorb the rest and give us an equivalent solution. The equation is equivalent to Helmholtz, to the standard discretization of Helmholtz up to discretization errors. And in order to apply this method, we need to make sure that the gradient of tau squared, the length of the gradient of tau is larger than the square of kappa. So eventually this term here moves from being indefinite to our side, to the positive side. Okay, so in this work we try to make the amplitude as smooth as possible to reduce the discretization errors. So we find tau by solving the Eikonal equation. We basically remove the omega squared term, and that has some physical consideration into this. So once the Eikonal is solved, we solve the ADR equation, which has no omega squared term. Only this, we are left only with this equation to solve. So there is a closely related approach by these papers. So they find tau by solving the Eikonal equation. They zero out the omega squared term, and they form a 1 over omega ansatz by zeroing out the omega term as well. So they zero out omega squared term and omega term, and they get this equation for A. Now, this equation does not depend on omega. It doesn't have the Laplacian, for example. It's a convection. It's solely a convection reaction equation, and it can be solved quite easily. But still, this is just an ansatz for large omegas, for really large omegas, and it doesn't capture the information about reflections. So you cannot impose sophisticated boundary conditions here. There are no reflections from the medium, basically for different parts of the medium. You basically get only first arrival information using this approach. So this is what we are doing. A depends on omega, and this is significantly different than this. So let's talk about the Eikonal solvers. How do we solve the Eikonal equation, which is given here? There is quite a zoo of papers and work on this. The method that I like the most is the first fast marching method. This is a really nice and sophisticated algorithm. It's not that sophisticated, but it is kind of a direct solver that solves the problem in order of n log n. Consider this as a single Gauss-Seidel sweep that really solved the problem. You just need to figure out the perfect ordering to do that. So this gives you a general framework to just solve it. There is a different approach called fast sweeping. This is basically Gauss-Seidel, lexicographic Gauss-Seidel. And well, these two approaches are applied to different versions of the problem. So you have the straight Eikonal, just the Eikonal. We discretize it using upwind scheme, and we have these solvers to use. Fast marching will always convert, like it solves the problem. It doesn't have convergence rate, it doesn't have iterations, it just solves the problem. It exists for first and second order approximations. Fast sweeping, we kind of enter the iterations regime. So if you solve for first order, then you'll need very few iterations. If you solve for high order, then you'll need more iterations. There is a Lax-Friedrichs formulation that adds this regularization term here. Then once you add that to smooth out the solution a little bit, you'll need more iterations. But still, all of this was not good for us in this particular problem. And the reason is because we have the gradient of tau and the Laplacian of tau in our formulation. So we apply numerical derivatives, so we need it to be accurate, really accurate. Now, look at this plot here. This is the solution to the Eikonal equation for constant medium. This is basically the distance function, okay, R. This has a singularity at the source, okay? And since when applying numerical derivatives by applying the numerical derivatives, we handle singular functions well. Like, it doesn't really work. So if I take this function, apply the Laplacian to it, I get something that is very different than the Laplacian, the analytical Laplacian of this equation. So the solution to handle these problems at the source would be to factor the Eikonal equation with the analytical solution to a constant medium at the source. So we define tau as the product of tau 0 times tau 1 times tau 1, and tau 0 is the solution to a constant medium. So we get, again, more versions of the problem. So again, we have the straight factored Eikonal, which again can be solved quite fast. This is not a very simple algorithm. There is the Lax-Friedrichs approximation that does the job really well in terms of the solution that it gives, but it takes forever to converge. So nothing really worked for us in this particular problem. So we liked fast marching so much, so we invented a version for the factored Eikonal for fast marching. It works with second order. It gives us the solution in a single sweep. And I'll just show you a movie, if I can get this to work. Okay, so you start with this in the source. You form a front that advances away from the source. It advances by proportional to the speed that is given by the medium. And once you visit a point, you know the solution to that point, so you don't visit it again. And so in every iteration, on every inner iteration, you find the solution to a single point, you iterate over all the points, and you get the solution right away. So this is kind of a single Gauss ideal. It requires a little bit of mechanisms to work, but that is solved. So once the Eikonal is solved, we solve the ADR equations, and first we'll talk about discretization. So we've got the Laplacian here, just central difference. The gradient here we can use central difference or second order upwind. And this is just a reaction term. This is a diagonal matrix times A. As boundary conditions, we can use the same boundary conditions that you would use for standard Helmholtz. So if it's Neumann or Sommerfeld, we have the equivalent boundary conditions. And then we use multigrid. So you know this slide. Now I'll say that multigrid is suitable for solving real-valued advection diffusion problems, among other problems, obviously. But here we have a complex value equation. So this is harder than the original, than the real-valued equation. So here, if you look at the spectrum of the gradient, it has a large imaginary spectrum, which together with I omega here brings us to an indefinite operator. On the other side here, you have a Laplacian. It's a diagonal matrix, but it may have negative and positive values. So it's indefinite, but then it multiplies with I omega, so it's a complex shift. So this becomes our friend, and this becomes our enemy. But still, we need to deal with that. So because we don't want to get into the indefinite problems in our multigrid V cycle, we use a first order upwind discretization as a precondition for second order gradient, which means that for each imaginary part of the gradient, we have also the shift from the first order upwind, so imaginary shift. So it kind of balances. So let's see some numerical results. First, I'm going to talk about accuracy. So we compare our formulation with standard second-order discretization of Helmholtz. We use a simulation that is related to seismic inversion. So we usually have this large domain because seismologists cannot see too deep into the ground. We've got this large domain. We would typically have boundary conditions here that simulate infinity. These are the ground boundary conditions because the ground goes to infinity. So we use an absorbing boundary layer here in these boundaries. But at the top layer, we've got basically air. So it's not like the ground goes to infinity. So we've got Neumann boundary conditions on the upper layer here. And the source is at the top row somewhere, and the receivers are also. So we have a source here, let's say, and we measure the solution here. So let's see some comparisons. First, we consider a linear medium that as we go deeper, the ground becomes more dense. And this is the solution for tau. It's kind of circles like that. This is the solution of the Helmholtz equation. This is the solution of our formulation, H is 1 divided by 1 divided by 1,000, so the domain is 1.5 by 0.4. And we've got 50 points per wavelength, so we've got a really good accuracy from both of the approximations. And if you look at the error here, then we've got 0.01 at really close to the source, where Helmholtz itself is not very accurate, but in the rest of the domain, we've got almost equivalence between the two formulations. Still, this is quite an easy problem to solve. You can see that the amplitude is smooth, so those of you who looked for smooth solutions to Helmholtz, it is pretty smooth. The amplitude is pretty smooth. Now we go to a coarser mesh, so H is 1 divided by 256. So we've got 12 points per wavelength, so this is kind of like the edge where the discretization still holds in terms of accuracy. In the eye, you can see that the solutions are pretty similar, but then you look at the error, you can see quite large differences at the top, right where we plan to measure our solutions. Get almost 0.1 difference, where the amplitude is also 0.1. Now, we get this error, but this is a comparison between Helmholtz and our reformulation. Nobody knows who is more correct, but let's do the experiment. So I'll solve the problem on a fine mesh, get an accurate solution. I'll solve the problem on a coarse mesh, get a semi-accurate solution, and interpolate the solution for the coarse mesh. So I'll get to see what's happening. So we've got in blue, we've got the interpolated Helmholtz solution. We've got in red our solution, which is interpolated. In green, you'll see the true solution for Helmholtz, or the fine mesh solution. And in black, you'll see the fine mesh solution for our approximation. And let me just zoom in here. And this is what you see. So in blue, again, the Helmholtz solution, the interpolated Helmholtz. In red, our interpolated. And in green and black, basically, is the true solution. They overlap because they're really close. So you can't really see the difference between them. What you can see is that Helmholtz has this shift. Okay, shift in the phase. So it gets the phase wrong. And once you get the phase wrong, you can see the error. So in blue, you see the error of Helmholtz compared to the true solution. And in green and in red, you see the error of our approximation. So we get the phase more accurately. Now, we get the phase more accurately because we solve the Eikonal equation, which gives us the phase. So let me summarize this. The discretization of the Eikonal plus ADR leads to a better phase estimation compared to direct Helmholtz. And this phase information is actually a lot more crucial for the accurate solution of the full waveform inversion of the inverse problem at the continuation of this work. Because you saw the errors that this brings. So this is just to show you. This is the same domain. H is 1 divided by 500, 25 points per wavelength. This is the Marmousi model, which is a highly, I don't know if highly, but this is the heterogeneous medium that we plan to face. And you can see the amplitude has some bumps in it, but it's still quite smooth. And this is the error. So you get 0.02 at worst, which is about 10% of the actual solution. So again, this is the difference between Helmholtz and ours. I believe that this is what approximately would be the error here in both options. Okay, so now we'll see some numerical results, how we actually solve this thing. So we compare our method with the shifted Laplacian method. This will both be our implementation. We use Galerkin type geometric multigrid, basically use bilinear interpolations. And multigrid is used as a preconditioner with flexible GMRes up to 5 orders of magnitude relative accuracy of the residual. in our method, we use K-cycles with FGMRes as the engine in the K-cycle, and we use Jacobi preconditioned GMRes relaxations. We do more relaxations on the coarser grid, so we do minimum of level 3 relaxation. So on the first level, we do 1, on the second, we do 2, and the rest will be 3. The shifted Laplacian, we use some combination of these papers. We shift by constant of half, and we do F11 cycles with Jacobi preconditioned GMRes. We basically get slightly better results from what the papers show, but we compare that in terms of timings, so we can really compare the two methods one by one. Each of these cycles cost about half of the K cycles. So, but I show timings as well, so we can have an idea. K cycles, they are basically W cycles. We have a call of K cycle here inside FGMRes. There is a threshold, so if omega is small and we solve the problem using V cycle, then this will reduce from W to V cycle. Let me skip that. It's W cycles for whatever it matters. So we start with the slope example, the linear medium, and here you can see 3 test problems. All of them are almost square domains. H is 0.004. H goes divides by 2, and H divides by 2 again. And here you see 3 frequencies. So the bottom of each 3 is the 12.5 grid points per wavelength. So that's the limit of the discretization based on this H. So what you want to see is kind of look at the WH scalability. So here you can see 43 iterations compared to 56. Here you can see 53 iterations compared to 90. Still, in terms of seconds, we're a little bit better. But here, at the larger scale, we get 51 iterations compared to 150. And the timings are much better. In terms of the other frequencies, we basically, at all cases, we solve the problem faster. At the intermediate frequency, we get a comparable solution, but again, the scalability is what's important here. Below the frequency, below this frequency, like if omega h is, I don't know, 0.1 or something, we get basically Poisson-like convergence. So 10 iterations, 8, 7, whatever. So this is the wedge model. And again, we see the same pictures. So again, 33, 32, 32 against 68, 119, and 150. So you can see also the difference in timing. So it's 79 seconds against 262. I'm not so proud of the timings, but this is just a simple MATLAB code, single core, whatever MATLAB uses in the sparse matrix package. So this is the Marmousi model, the last test case. And again, we see the same results. So 41, 49, and 58 compared to 60, 90, and 144, and our timings are better. And again, below, let's say here, below 20 hertz here, we solve the problem really, really fast. So let me conclude. We proposed a new method for solving the Helmholtz equation for a point source. The method is based on reformulation and reformulating and splitting the problem into the Eikonal equation and the ADR equation. We solved the Eikonal equation for the travel time based on factored fast marching, which is a very, very nice algorithm. And we solved the ADR with Multigrid. The reformulation is equivalent to Helmholtz up to discretization errors. And actually, we get the phase more accurately for high frequencies, which is very important for us in seismic inversion. The multigrid performance is good, very good for low frequencies. It is okay for high frequencies. It is, you can say that it is match independent, but it is not as good as you would want eventually, considering that the solutions are indeed smooth. In the future, we plan to implement this in 3D and go to the inverse problems where we have more problems to deal with other than this, although this is the main one. So thank you very much, and I'll be happy to answer any questions you might have.